Good afternoon and Happy New Year. Welcome to our first office hours of 2021. Hope everyone had a good and relaxing and safe holiday. My name is John Kowalski. I'm part of the marketing team here at Vic Gardner. And today's presentation is on the fundamentals of color theory. If you're unfamiliar with our office hours format, let me tell you how it's going to work. We have our resident technical expert, Corey Cohen. He's going to be presenting today for about 20-25 minutes maybe, more of an abbreviated presentation. And then after that, we will open it up for questions, comments, discussion. So located in the bottom right-hand corner of your screen, you'll see a Q&A box. Just log in any questions you have, and we'll get to them in order immediately following the presentation. Also, we are recording this, and tomorrow you'll receive not only the presentation that Corey's going to go through, but also a link to the recording, so you can listen to it again, share it with colleagues, or entertain your family. That's good too. So with that, Corey, let me turn things to you, sir. It's all yours.
Thank you, John. Good afternoon, everyone, and Happy New Year. Thanks again for joining us for our first office hours of the new year. So today's topic will be one of my personal favorite, perhaps my favorite topic, color theory, which is just how we see color and how we translate that knowledge into being able to measure color and match colors and view colors visually and things like that. So today we're just going over the basics of color science. Of course, in future office hours, we will be going more in depth into certain advanced and specialized topics like improved difference methods and different types of spectrophotometers for different surfaces and things like that. But today this will just be basic color science, so it'll be great for anyone who's new to color and maybe needs a fairly quick overview, or anyone out there who might need a refresher. So let us get started. So first of all, why do we need objective color control? There are a few good reasons. One is that color perception is subjective. It depends on who's doing the perceiving. It can depend on things like age, just like with all of our other senses. You know, our hearing tends to get worse over the years, our vision fades. So too does our color vision. So typically young people tend to see color better than older people. Gender can affect how we see color. It's widely believed, and there is some genetic evidence for this, that women can actually perceive more colors than men, more different shades and hues of colors. And even our moods can affect how we see colors. So, you know, if we're feeling really angry, we might be we'll say that we're seeing red. If we're down, we might say that we're feeling blue. And there's some truth to that. Our emotions actually do affect how we see color. So color perception is fairly subjective. Another good reason is that we have a lot of trouble communicating and remembering colors. We have trouble communicating colors because there are only so many words we can use for describing colors or describing the differences between two colors. We can say that, you know, a color is red or blue or green. We can say that it's dark or light. But there are only so many ways we can describe it. At a certain point, we want to quantify color so that we can analyze it in a more scientific way and be able to communicate that with other people. And our memory for colors is also not very good. So there's a statistic that's often cited out there that we are capable of perceiving something like, depending on who's speaking, it'll be between 6 and 10 million different colors, which is true. We can perceive approximately that many different colors, somewhere in that millions of colors range, but only if they're side by side. The thing is, our memories for color are very, very bad. So I can take two panels, take these panels in this picture that this guy is looking at here. One is you know, a little darker than the other. The one on the left might be a little more chromatic. So clearly, when we're looking at them side by side, we can see a very clear difference between these two panels. But if we were to separate the panels, let's say we take one of these panels and put it at one end of a long room and take the other panel and put it at the other end, if I walk to one and I analyze the color visually, and then I walk over to the other, by the time I've walked to that other color, my memory for that original color has faded. So our memories are very, very bad for remembering exact shades of color. When they're side by side, they're easy to differentiate, but we can't hold that exact shade in our memory. And color is also dependent on surrounding light and background. And so things, there are a lot of things that need to be controlled for in order to have objective color viewing or color evaluation, things like the light source, the light level, the illuminant, as well as the ambient colors, things like that. So objective color control is needed for all these reasons. So one good reason to control for your color is that color stands for quality. So here we see all these Coca-Cola bottles sitting on these shelves, and this was actually part of an experiment where they took some white-capped bottles. You can see one sort of front and center in that middle row, but there are a bunch of white-capped bottles here, a few white-capped bottles, and studies show that those are going to be the last bottles left on that shelf. And that's because consumers associate consistency with quality. So nobody wants the oddball bottle that has the white cap because that one looks different, so maybe it tastes different than the other ones. So consistency is key when uniformity and consistency is key for consumer products. And this is especially important for multi-component products. And these are products where you have different components that may be manufactured and or painted in different locations, sometimes even by different companies. And then it's shipped to a central location to be all put together, and whatever the final product is, whether it's an automobile or a vacuum cleaner or a laptop. But so when you have all these different parts that are fabricated in these different locations, you have to make sure that they're going to look good when they all come together. So it's especially important when you're taking different parts manufactured in different locations that you control for the color and the overall look of all those parts so that the final product will look good once assembled. So here we just have just sort of a little optical test. So the question being presented here is which of these squares is darker, that A square or the B square? Now to my eye, that B square looks lighter than the A square. The A square looks darker. But if we cut out the middle and we put them together, we can see that these two squares are actually the same color. So this is sort of our eye tricking us into believing that these are different colors when they're actually the same, because our eye sees that B square in that first picture as being under the shadow. And so our brain tries to compensate for that and says, well, that color is actually lighter than it appears, because if it wasn't under the shadow, it would look lighter. But of course, this is just a 2D static image. So if we take the B square and put it right next to the A square, they are actually the same color, despite them looking very different in that first picture. So here's another one. We have some colored lines, and then we have some different colored balls. But if we remove the lines, what we see is those balls are actually all the same color. So it's just sort of these lines that are strapped across them that are sort of giving us the illusion that these balls are red or green or blue, when in fact they're all sort of a yellowish color. So this is another way of sort of tricking our mind and tricking our eye into thinking that something is something that's not. Okay, so this is why objective methods are necessary. We need instrumental color measurements so that we can quantify color in a repeatable and precise way in order to be able to evaluate and communicate color. Okay, that's it for sort of the introduction to this little presentation. So now we're going to get into the thick of it. So when we talk about color perception, we talk about the three components of color perception. That is object, light source, and observer. So in order to measure color, in order to quantify color, we need to understand how we perceive color. And in order to understand how we perceive color, we have to understand each of these three components. So we're going to start with the light source or illuminant. Those terms are somewhat interchangeable, somewhat not. They do have distinct definitions, but we'll get into that a little bit later. So what light is simply an electromagnetic wave. Same as radio waves, same as gamma rays, X-rays, whatever. It's all the same stuff. The only thing that differentiates it is the wavelength, or the range of wavelengths. So this specific range of wavelengths in the electromagnetic spectrum, this is the only range of EM waves that we can actually see with our eye. From 400 to 700 nanometers, our eye can perceive that, and we can't see anything outside of this range. So this range of 400 to 700 nanometers makes up what we call visible light. And the color of light that we see depends on the exact wavelength. So we can see from this little diagram here that if we're down at the low wavelength, then we start with violet at about 400 nanometers. As we get up into 420, 440, 460, we're looking at blues, different shades of blue, different hues of blue. And as we get into higher wavelengths, we see green, yellow, orange, red. And so if you take all of these wavelengths of light, all of these different colors of light, and mix them together in approximately equal amounts, what you get is white light. So white light is just a mixture of all the different colors of light. Now, if you have a white light or a whitish light source, you can take that light, and there are ways to split that light into its component wavelengths, such as by shining it through a prism or some sort of diffraction grating. So if we go down into the shorter wavelengths, we get into UV, ultraviolet, which is invisible to us, but it can play a role in fluorescence, which is a different office hours. And then if we go into longer wavelengths, longer than 700 nanometers, we get into IR or infrared, which of course is also invisible to us. So here we have a set of what we call standard illuminants. So I mentioned there is a subtle difference between illuminant and light source, although they're often used interchangeably. A light source is actually a physical object that emits light, such as a light bulb or a lamp. A lamp is a light source. An illuminant is actually just a set of values that make up what we call the spectral power distribution of one of these standard illuminants. This was established by the organization CIE, which in English stands for International Commission on Illumination. So they standardized these various illuminants that mimic different light sources in everyday life. So here, for example, at the top left, we see the D65 illuminant. There are several different D illuminants. They're all meant to mimic different types of daylight. So D65 is likely the most commonly used type of daylight. And so we can see the spectral power distribution below it, that curve that shows us the relative amounts of each wavelength. So we can see that this D65 is a fairly even white light source. It's a little heavily weighted towards the blue, but it's a fairly white light source as opposed to that A illuminant that we see in the middle, for example. We can see from the SPD, the spectral power distribution, that it's very heavily weighted towards the longer wavelengths, the yellows and oranges and reds, and that's going to give this light source or this illuminant a sort of orangish hue, a warm hue that you might remember. We don't really use tungsten bulbs in our homes anymore, but if you remember, they tended to give off kind of a yellowish warm hue, and that's because of the heavy weighting towards the longer wavelengths in that A illuminant. And then we have F2 to the right, which is an example of a fluorescent illuminant. So fluorescent illuminants tend to be characterized by these big spikes in their spectral power distribution, which of course you can see here in this curve to the top right. And so the whole point of this is that colors are going to look different under different light sources. So if we want to standardize color evaluation, if we want to standardize color measurement, we need to determine what illuminance we're measuring at. We need to be consistent with which illuminance that we use so that we can compare data with other people. So here's an example. So there is a phenomenon called metamerism. Now, metamerism is when you look at two different objects under one light source and the color appears to match. But if you look under those two objects under a different light source, the color does not match. That's called metamerism. And you can see here the reason for that. So in the middle here, those curves we're seeing are what we call the spectral reflectance curves for these cups. So this is the quantity of each wavelength that's reflected by the color. And so we can see that these spectral reflectance curves are slightly different for these two cups, even though they're a pretty much perfect match under D65, because of the difference in their spectral curves under a different illuminant, they might not match so well. And we can see that the A illuminant is going to sort of exacerbate the differences in those spectral curves, particularly in that longer wavelength range where there's a lot more of those wavelengths in the A illuminant than the D65 illuminant. And that's going to cause a mismatch when we're looking at these two cups under the A illuminant. So this is why illuminant is so important, because you need to, when doing color measurement, you want to be using the illuminant that most closely matches where your product will be used in real life. If the product is used outdoors, you want to use D65. If it's maybe used in an office building, you might want to look at fluorescent illuminants and things like that. So the illuminant does matter when it comes to color evaluation. Okay, so we know about the light source. Now we're going to talk a bit about the observer. So the observer, of course, is us. It's our eyeball, our apparatus for perceiving the light all around us. And so our eye has two different types. There's a bunch of different types of cells in our eyes, but there are two types in particular that are responsible for our color vision. And those are the cone cells and the rod cells. So the cone cells are our color detectors. They are each sensitive to a different range of wavelengths. They come in three main flavors: red, green, and blue. And so the red cone is sensitive to wavelengths in the red range. The green cone is sensitive to wavelengths in the green range, and the blue cones are sensitive to wavelengths in the blue range. And it's the combination of the signal from each of these three types of cones that allows us to see all the different colors that we're capable of seeing. And then, of course, we have the rod cells, which are lightness detectors. So those rod cells aren't differentiating different wavelengths. They're just telling you overall how much light there is. So if you've ever noticed when you're in low lighting conditions, you're maybe sitting at the movie theater, the lights have gone down, you can kind of still see, but not in any great detail. You might notice that everything you see tends to be in blacks and whites and grays. And that's because once the lighting levels get low enough, there's no longer enough light for those cone cells in our eyes to work. And so our eyes just shut them off and we see by the rod cells only. And that's why in low lighting conditions, we only see in shades of gray. We can't make out color. So in order to quantify color like we want to, we need to understand a bit more about those three types of cones in our eyes. Specifically, we need to know what are the exact sensitivities of each of those three cones. Which wavelengths are they sensitive to? So in order to determine that information, an experiment was developed by these guys, Wright and Guild, the Wright-Guild experiment. So the way this went was that you'd have a test subject behind a masking screen, and that test subject would be looking onto another screen on which would be projected some colored lights. So there's a partition separating the two sections of the screen that the test subject is looking at. On the top part of the screen, you're getting the three primary colors that correspond to the cones in our eye. And on the bottom part of that screen will be projected a colored light source. And so it was the test subject's objective to adjust the power level, the relative power levels of those three primary colors on top until the mixture of those three light sources matched with that light source on the bottom. And so by repeating this experiment with many different colors and different test subjects, scientists were able to determine the sensitivities of those three types of cones in our eye. Now there are two versions. Those are what we call the observer functions, those sensitivity curves. We're going to see those in a sec, but there are two different versions of the observer functions. There first was the 2-degree observer developed in 1931. And this is where the observer would be looking, they'd be analyzing those colors from the previous slide using a 2-degree field of vision. So color would hit a fairly small area of the retina. And the purpose behind this, the reason they decided on such a small field of vision, was that it was believed that the cones that detect color in our eye are more concentrated towards the center of the retina. And as you go outwards, you're getting more rods. And they wanted to isolate the cone cells so that the light would mostly only be activating the cone cells, thinking that would produce better color viewing. But they found out that really wasn't the case. So in 1964, they redid the experiment using a 10-degree field of vision, and that light hits a much larger area of the retina, and they found that corresponds better with color viewing. So the 10-degree observer functions are almost exclusively used today. There are still a few applications for which the 2-degree observer is used. Yellowness indices are one common use for those. But typically for most color measurement, it's the 10-degree observer. If you want to visualize what that field of vision looks like for each of these, if you take a quarter and you hold it out at arm's length, you're looking at about a 2-degree field of vision by looking at that quarter. And similarly, if you want to simulate a 10-degree observer, you could take a tennis ball and hold that out at arm's length, and that would represent about a 10-degree field of vision. So this is what those observer functions actually look like. So these are curves describing the relative sensitivities of each of those three types of cones in our eye. So we can see that the sensitivity of the blue cone maxes out, peaks somewhere around 450 nanometers. For the green cone, it's somewhere around 550, and for the red cone, it's a little over 600. So each of these cones, again, is sensitive to a different range of wavelengths. And so it's the combination of the signal, the amount of light received by each of these three cones that allows us to differentiate all the millions of different shades and hues that we're capable of differentiating. So back to our three components of color perception. We've discussed the light source, and we've discussed the observer. So now we're going to talk a bit about the object. So when light hits an object, what happens? So a few things are going on here. One is that you're going to get a direct reflection off of the surface of the object, and that's what we refer to as gloss. You're also going to get some absorption. Some of that light is going to penetrate the material and interact chemically with the pigments in the material. And the pigments, their job is to selectively absorb wavelengths. So some wavelengths, when that white light hits them, some wavelengths are absorbed, some wavelengths are reflected in various amounts, and it's that reflected combination of wavelengths, that reflected spectrum, that gives an object its color. So in this case, it looks like these are orange pigments, so we would say that this pigment is absorbing most of the shorter wavelengths, the blues and the greens, and is mostly reflecting the longer wavelengths, the yellows and oranges and reds. And then what happens after that light interaction with the pigments is that light is going to be diffused. Rather than bouncing off the surface and at the opposite angle, or what we call the specular angle, as with the gloss reflection on the left, that light that has undergone pigment interaction is going to be diffused. So here again, we have an image of a surface. We have light hitting it. We have our specular reflection, or our gloss reflection. Now this is where if you were to be standing there, standing where that arrow on the right is pointing and looking at that surface at that angle, what you'd be seeing there is glare. That's what that specular reflection is. It's glare. Whenever you're seeing glare on a surface, it means you're viewing it at the specular angle. You can also see that the that arrow indicating the light source, it's that same rainbow color reflecting off as it is hitting the surface. And what that's indicating is that there actually is no pigment interaction at that specular angle. So that specular reflection is going to have, that light is going to be the same color as the incident light, that's the light source. So this is why even on a pigmented material, when you're looking at that gloss angle, when you're seeing that glare, you're just going to see a white reflection or a reflection of whatever the light source looks like rather than what the color of the object is. So you don't want to measure or analyze color at that specular reflection. You want to analyze color at the diffused reflection. So remember that light, some of it is going to penetrate the surface and reflect off at diffuse angles, and that's where we measure colors. So if we want to measure color here, we would place our observer or our detector at one of those diffuse angles in order to analyze the light that has interacted with the pigments. So when we measure color, what we end up with is what we call a spectral reflectance curve. And this is sort of the raw data, the primary data that is collected by a color instrument. And this, again, just tells us how much of each wavelength is reflected by an object and how much is absorbed. So here at the top left, we have a lot of reflection in the blue range and very little reflection anywhere else. So this is a blue color. At the top right, we're getting just a little reflection in the blue range, but almost all of our reflection is coming at the very high wavelength range, and that's going to give us a red color. At the bottom left, this spectral curve is peaking in the green range and decreases drastically as you go outside that range. So this is going to be a green color. And then at the bottom right, we have some blues and green, more of the yellows and reds. This is going to end up being a yellow color. So the building blocks of color, we now know about the illuminant. We know about the observer and how our eye works. And we know what's happening when light hits an object. So when we take all of those three things and we can quantify all those three things and put them together, we can use that to calculate color scales such as XYZ or LAB. This is referred to as CLAB or CIE LAB. This is the same CIE that standardized all those different illuminants. So what they did is they also came up with what we call a color space. This is a three-dimensional space where you can describe any color using three values, an L value, an A value, and a B value. So the L value stands for lightness. So the higher the L value, the lighter your color is. The A indicates how much red or green there is in your color. So a positive A value indicates the presence of red in the color. A negative A value indicates the presence of green. If the A value is very low, that means it's neutral. Similarly, the B axis is for blue and yellow. If the B value is positive, that indicates yellow in the color. If the B value is negative, that indicates blue. And so again, if the B value is close to 0, that would be neutral on that axis. So if the A and B value are both close to 0, that would indicate a neutral color like a gray. So in addition to LAB, we can also use a different set of coordinates to describe a color in this same color space. So we can use polar coordinates, LCH, as well as LAB to describe the same color. So it's the same color space. You can describe the same colors in this space. It's just two different coordinate systems. So for LCH, L is exactly the same. It's the lightness value, the vertical axis. But now instead of A and B, we're using chroma and hue. So chroma is how colorful the color is, or saturation is a term that's sometimes used. You might say high chroma colors are very deep colors, or just very chromatic colors is how we would describe it. So an example of a high chroma color would be like a scarlet red, or like a forest green, something with a lot of chroma in it, and something with a very low chroma value, an achromatic color, would be an off-white or a gray, like a beige or something. So the C value tells us how deep or how colorful our color is. And then we also have the hue angle, H. Now this can be a little difficult to understand for people just starting out, but the way the hue angle works is if you imagine the AB plane, this plane here as being a circle, beginning with the positive A axis being 0 degrees. If you move counterclockwise around that circle, the angle is increasing. So the positive A axis is 0 degrees. The positive B axis has a hue angle of 90 degrees. The negative A axis has a hue angle of 180 degrees. And the negative B axis has a hue angle of 270 degrees. So now we're using this angle as well as the chroma value to describe the position of our color on this plane. So here I have an example, just so you can see this in action. So we have our LAB. So here the L value is 58, so kind of a medium light color. The A value is positive 30.41. Remember, positive A indicates the presence of red. So there's a good amount of red in this color. The B value is positive 36, so there's a good amount of yellow in this color also. So we're looking at a color of medium lightness with a lot of red and a lot of yellow. When you mix red and yellow together, you get orange. So this color that you're seeing here towards the top right, whoops. Forgive me, technical issues. So this color we're seeing here at the top right is what's indicated by this set of color coordinates, this LAB coordinates. So when we measure color, when we quantify it in this way and we get our set of LAB values or LCH values, what we're really interested in doing is we want to know the difference between two colors. And so in order to do that, we have to measure the color of both of the colors that we're comparing. We generally refer to these as a sample and a standard. The standard is your target color that you're trying to reach, and the sample is your production color or whatever. And so you're measuring the color of both. You get two sets of LAB values, and then in order to determine the color difference between sample and standard, you're going to subtract one from the other. Sample minus standard, so you get a delta L value, the difference in the L values, delta A value, the difference in the A value, the difference in the B value. And then we like to put that together in what we call the overall color difference. And the simplest form that takes is what we see here, the delta E star value. That's how we refer to this. And this is simply a distance in color space. So if you calculate the distance between 2 points in color space, that's the delta E value. And to get there, you just take the delta L value and square it, add it to the delta A value squared and the delta B value squared, and then you square root the whole thing in order to get the delta E value, which is an overall color difference. So that's it for this presentation. Of course, there are many different more advanced specialty topics we could go into. As mentioned at the beginning, there are improved difference equations, there are different color instruments to talk about, and different applications and things like that. So we will get into all that stuff in future office hours. But for now, we are going to open this up to a quick question and answer session. So for that, I will hand things back to Jonathan.
Thanks, Corey. Good stuff there, a lot of stuff, that's for sure. And if anyone has any questions, please log them in the Q&A box located in the bottom right-hand corner of your screen, and we'll get to them. Right off the bat, Corey, what's the best way to describe color? What color system? The LAD, C-Lab? What is your thought? You there, Corey? Or did we lose him?
There.
Sorry.
Thanks, Ray.
Oh, go ahead, Corey.
Sorry, I started and I didn't realize I muted myself. Yeah, LAD is the most commonly used system out there, LAD and LCH, which again, it's the same numbers, just a different way of describing them. And which one to use actually depends on whether your color is chromatic or achromatic, or at least which one we would recommend using. So typically for what we call achromatic colors or near neutral colors, which we typically define as colors with a chroma value less than 10, we recommend using LAD. If your chroma value is greater than 10, we would refer to that as a chromatic color, and we typically recommend using LCH for that. And the reasoning for that is something I'll go into in when I talk about improved difference methods, but it has to do with tolerancing. Tolerancing becomes easier for achromatic colors when using LAB and for chromatic colors when using LCH.
Okay, thank you. Another question here. What industries still use 2-degree observer?
So again, that's mostly using yellowness scale. So I want to say weathering probably is largely where that's used, where you take your product and you want to see how well the color or the gloss or whatever stands up over time. And so you might use an accelerated weathering machine, or you might just take it and set it outside for a while to see how it ages, under the sunlight and the outdoor weather. And so typically colors often get more yellow when that happens. Specifically white colors tend to yellow over time when they're weathered. And so when using a yellowness index, there are certain ones that call for using the 2-degree observer.
Okay, thank you. I have a question here. Go ahead, Ray.
Also the ink industry, because everything's so small and you look at it so closely, they use 2-degree observers for ink industry too.
Mm.
Okay. Another question here from Andre. How much training in days or hours is required to become somewhat proficient with working with colors?
Ooh, hard to say. I mean, true color experts. We always, of course, advocate for instrumental color measurement because, again, that is the most objective way to do it. But there are companies out there that have that one employee who's been doing it for 30 years, and he's that one guy who can accurately match the color and determine what extra pigment needs to be added and all that. So it takes years or decades to truly become a pro at it. As far as just being trained to evaluate colors effectively, that's something that we can help with. Generally, we do sell light booths, and we can give you some guidelines on how to, and some training on how to view colors. Things like when you evaluate colors, you need to do it very quickly to avoid what we call color fatigue. So that's an issue and things like that. So I say to become effective in evaluating colors, probably a very short time, but to become a true master at it takes years or decades.
Okay. How old are you, Corey? You're a true master? You started early,
very
right?
Cool.
Yeah. Okay, another one from Ken. When do you still use the XYZ system?
Ooh, XYZ. Almost never. So there is one type of measurement that's often called overall reflectance, or it's sometimes referred to as reflectivity. And it's just a measure of, if you want to basically know how light your surface is, what the total amount of light that's being reflected by it is. You're not concerned so much with color, but just by the overall amount of light being reflected. And that's the capital Y value in the XYZ. So that is still often used for the overall reflectance measurement. As far as using the full set of XYZ, it's very rare. Sometimes you'll see specifications entered in XYZ, particularly like you might see it in ASTM methods and things like that. For example, if anyone's familiar with Gardner color, it's a set of color standards that are defined by X and Y values. So it's sometimes used there. As far as color measurement goes, though, very, very rarely XYZ is used altogether.
Okay. Question here from Martin. Are there any books or literature you can recommend to review all the basic concepts on color theory?
Ooh,
I know we have a lot of things on our website, byk-instruments.com. There's a whole knowledge section of videos, white papers, things like that. So that probably has some things. I haven't been out there in a little bit, but I'd check that out. But any books you recommend, Corey?
Really the best way to get training in this type of stuff is to attend webinars like this and things like that, or by just talking to us in person. But there is one book, and unfortunately I can't, I remember reading it when I first started with BIC. It's a bit technical. It goes into the history of the different color scales, a lot of the pre-LAD color scales, kind of giving an understanding of how we got to where we are. But I could send you the name of that book once I find it, if you'd like.
Okay. Yeah, that'd be great. That'd be wonderful. Another question here from Brian. My company paints plastic parts used on recreational vehicles. We use automotive level paints and currently use C-Lab 1976 formulation for color difference. Would it be better for us to switch to the CIE or fluorescent type colors?
That last part gets me because I'm not sure there actually is a difference method for a color system specifically for fluorescent colors. We do have instruments that can measure fluorescent colors, but the output is still just in LAD values, as with typical colors. But so typically we would recommend, if we're talking about solid colors, we would recommend one of the more advanced color difference methods like Delta E 2000. If it is in what we call an effect color, like if there's metallics in the color that give it that sparkle effect, there are different, first of all, there's different instrument. You need to use a multi-angle instrument for that. And there are different color difference equations, different color systems specifically for those type of effect pigments. So which one to use would really depend on what exactly it is you're painting, what type of paint it is, and what exactly it is you're measuring, but also what's being specified. So typically in situations like this, there might be someone that is specifying what needs to be used, what scales need to be used, what needs to be reported as far as the color measurement. So if you'd like to discuss that further, I'd encourage you to reach out to us directly, and we can figure out what you need.
Okay. Brian, I'm going to unmute you here. Did that answer your question? I know there's lots of variables.
Yes, for the most part.
Okay.
We have some colors like your aqua blues, some lime yellows, and we've had trouble color matching simply because we're not, I believe because we're not taking into account the chroma. Whereas the 2000 method would do that for us.
Yeah, yeah, definitely. There's certain colors are going to be more difficult to match just because our eye, some colors our eye isn't able to as easily differentiate, and so we have a little more tolerance for those colors. And some colors our eye is very easily able to differentiate small differences, and so it can be harder to match those colors. But yeah, the Delta E2000 and those improved color difference equations, the whole point of those is to try to account for things like that. So if you'd like to discuss that further, again, you can reach out to us, or you can wait for our webinar on color difference methods.
Okay,
Yeah.
thank you.
Okay. All right, thanks, Brian. Okay, another question here from Todd. In your mug slide showing the reflectance curves, can you explain more about why the yellow mug is yellow based on the reflectance spectra showing reflection in blue, green, and orange, red?
I mean, it's hard to get into too much just based off of a spectral reflectance curve. But really, I mean, spectral curves in general are more complex than what you're seeing here. They tend to be fairly chaotic mixes of wavelengths, so it's not always as easy as, you know, this one on the top left where there's a big spike in the blue range and then almost no reflectance anywhere else, and so you know this is a blue. Most colors are a pretty chaotic mix of wavelengths that just the mixture comes out in the way it does. So yellow is a fairly light, or typically is a fairly light color. If it's too dark, we typically refer to it as like brown. So yellow would typically come from a color that's exhibiting a lot of reflectance. And so on that front, you can at least see that there's more reflectance in that yellow color than anywhere else. But yeah, colors are just a mix of wavelengths, and it can be difficult to read what it is exactly just based off of the spectral curve.
Okay, thank you. Todd, I'm going to unmute you here, sir. Did that answer your question?
Yeah, I think that kind of covers it. I guess your answer, if it's just more complex than kind of those other examples on there. Yeah, I'm pretty new at this, so I haven't seen a lot of these reflectance curves and tried to decipher what they translate into.
Yeah, gotcha. Definitely reach out to us. You know, you'll get an email with this presentation as well as the recording link that you can listen to. But if you have any questions, just reply back to that or reach out to us, and we'll get in contact with one of our technical folks or regional folks, and they can help walk you through any questions you may have, or, you know, other information you need. So thank you.
Thank you.
Another comment here from Christopher. No questions, but thanks for the refresher course, since it's been years since the last time, and I'm now working directly with color. So congrats on that, Christopher. Welcome back. Another question here from Margie. What is the difference between delta E and delta E CMC? I've heard delta E CMC is also an overall measurement of color accuracy, but I don't understand the difference between the two.
Okay, so I don't want to delve too deep into this, but I can at least show you. Let me see if I can. Okay, so here we go. So the idea behind this graphic is that in the center, you have all these shapes, these sort of circular elliptical shapes, and in the center of each shape is a little dot. So that dot is a standard. In each case, that dot is a standard, and the shape drawn around it indicates the limits of perceptibility. So any other color inside that shape would be imperceptible. There would be no difference to our eye between any other color in that shape and that dot in the center. But any color outside of that shape, we'd be able to see a difference. So the point of this is that you can see that these tolerance shapes vary across color space. They're different sizes and shapes depending on which color you're talking about. So you can see like these at the top right, if you look at those sort of reddish orangish colors versus on the left, looking at those greenish colors, the green tolerance shapes are much, much fatter. And so this indicates that we have a higher tolerance for green colors, meaning our eye isn't as good at differentiating small differences between green colors. And that's why those shapes are very fat to the left. They have big tolerance shapes because we're not as good at differentiating them versus the tighter ones at the right, where our eye is very good at differentiating them. And so any small color difference is going to appear much larger to our eye. And so the point of these improved color difference methods is to make this color space more uniform, such that the ultimate goal would be to have a perceptibility tolerance, or at least an acceptability tolerance of 1, rather than having to have a different tolerance for every color. So for example, if I was going to set up my tolerances for one of these green colors, I might be able to set my delta E to 3, because that's how much leeway I get with the tolerance. Even a delta E of 3 isn't going to be very visible to me. But if I look at those colors towards the center that have that much smaller tolerance shape, I might need to set that at 1 or even less, because that would indicate a similar color difference. So the point is that we want to make a delta E of 1 the same visually, whether we're talking about a green color or a gray color or an orange color. And so that's the whole point of these improved color difference equations, like delta E, C, and C. These were developed to try to make that happen, to make color space more uniform. So if you're having trouble, with the previous question, I mentioned this a little bit. If you're having trouble with some colors where the same delta E looks like a much larger difference for certain colors than for others, yes, you might consider switching to one of these improved color difference equations like delta E, C, and C, or 2000.
Okay. Margie, or Margie, I'm sorry if I'm mispronouncing that. I'm going to unmute you here. Did that help clarify a few things for you or create additional confusion? Margie, are you there? Might be having some audio issues. I hope that answered your question. Another question here, too. What's an example of what happens when there is metamerism in automotive?
There's metamerism in automotive. Cars are almost always viewed outdoors. I guess there would be a difference between, say, daylight at noon and horizon light, so that it's possible there could be metamerism. Ray, is that something you can comment on?
So the biggest thing we've seen in automotive is that when they pull the cars into the showrooms and they have fluorescent lighting and no one looked at metamerism, that then you can have a mismatch because everything, like Corey said, is looked at under daylight. So that's where the biggest problem happens.
Mm-hmm.
Okay, what other questions? We've got through all the questions. Are there other frequently asked questions that you get, Corey, or any of the regional sales reps or business line managers on the line?
The one thing that I would say is, like, when we talk about color, we should talk about hue, then chroma, then lightness, because that's how we see it. So a lot of times, like Corey was saying, like communicating color is really hard. And if we kind of try to get the industry to talk in the same manner, I think that would help a lot too.
Mhm.
And then, of course, if anyone, you know, is having issues with measurement and it not matching what they see, we can definitely come in and figure out what equation we think might better apply to whatever they're doing.
Okay. I just got a new question in here from Fernando. What color quality assurance properties should basically solid industrial products be checked for? Is gloss included?
Yeah, we recommend for solid objects, color and gloss are both good things to check because gloss can affect how we see color. We see glossier surfaces as being darker. And so you want to make sure that all your products, in order to be uniform, are not only close to each other in color, but in gloss as well. And this is actually why our handheld spectrophotometers for solid color come with a built-in 60-degree gloss meter. You can measure both at once.
Okay. Fernando, did that answer your question? I'm going to unmute you here. Are you there, Fernando?
Yes, yes, thank you. Thank you very much. So I have another question, just basically to take advantage of this. Is there any standard that indicates that the delta E is good enough to approve industrial color delta E below 1?
The problem with using just a delta E, I assume the delta E star, the basic distance and color space formula. The problem with just using that as your tolerance is, again, you know, what I was saying before, where delta E of 1 for a red color may look like a huge color difference, where the delta E of 1 for a green color may look like a very, very small difference. So if you're using delta E star, you kind of have to go around and determine what the acceptable tolerance is for each individual color. And that's one of the main benefits of using those improved color difference equations like you see here, CMC 94-2000, because the goal is to have just one tolerance for all your colors.
Okay.
So if you use C-Lab, you have to actually go to individual color and adjust your tolerancing. So it's going to be different for every.
Gotcha. Thank you.
Yeah, and feel free to follow up with any of us for some, you know, training or additional information if you need it. Thank you. Okay, let's see. Another question here. Does a spectrophotometer need to use the same illuminant for the color that will be viewed in for its end use?
Okay,
I'd say yes.
so for one, yeah, I mean, that's always preferred. First of all, I want to make sure you're not confusing the terms illuminant with light source, because again, those are different terms. So the light source that an instrument uses as far as the color calculation doesn't really matter. So light source isn't actually going to use D65 or A or whatever illuminant is being selected. It's just using a generic white light source to measure spectral reflectance. And it's after that measurement is done that the illuminant data, you know, how much red or green or blue, you know, how much of each wavelength is in which illuminant, that data is applied to those measurements afterwards. So you can calculate your color values based on any illuminant that you want.
Todd, I'll unmute you here. Did that help or any follow-up?
Yeah, that answers the question. I wasn't I'm not familiar enough with the spectrophotometers to know what light source is used in those, but it sounds like it's kind of a generic one that then you apply the values of your end use illuminant to that to get your color value. I think I understood the answer.
And you can do any illuminant that you want because it's just an equation.
Yeah, okay.
So if you wanted to do like 3 different illuminants, you can also do that.
Thank you.
All right. Thank you, Ted. All right. I think we're all through the questions. The hour's up. We appreciate the lively discussion, everyone's questions and input. I hope you found this worthwhile and informative. As I said, we'll be sending out the follow-up information, this presentation, as well as a link to the recording. That will be in your inbox sometime in the morning. And with that, stay tuned for new topics and office hours, as well as our normal 60 minutes presentations coming out. And as always, if you need anything, don't hesitate to reach out. We'll get you in touch with the right people. So with that, have a great afternoon, and thank you, everyone. Thank you, Corey.
You're welcome. Thanks, everyone. Have a good night.
Thank you.